Hello students, I am A.K. Dubedi. Welcome to part 8 of our chemical bonding series. Today we are going to talk about chemical bonding and molecular structure. The 8th part is resonance. The learning objective of resonance: define resonance and resonance structure. Second point is explain the concept of delocalization of electrons in a molecule and draw resonance structure for the molecules such as benzene, ozone, nitrate and carbonate, and compare stability of molecules based on resonance energy, and identify with the actual structure is a resonance hybrid rather than a single canonical form. And next point, formulate resonance structure for the polyatomic ions or conjugated system. This learning objective is explained based on Bloom taxonomy. It is very useful and helpful to understand the concept of resonance. So, resonance may be defined as the phenomenon in which two or more structures involved in individual position of atom can be written for a particular compound. For example, in benzene ring, in this ring alternate single and double bond and delocalization of pi electrons, the movement of pi electron one position right or left. This structure indicates the pi electrons are not localized, pi electrons are delocalized. Similarly, in case of acetate radical, CH3 C double bond O and O minus, minus because after the removal of H, oxygen acquire a negative charge. Due to involvement of electron, the structure becomes CH3 C double bond O. Again delocalization of pi electron. In case of cyclobutene, these two positions acquire a positive charge. Movement of this electron means pi electrons shifted in this direction and these two positions acquire positive charge. Again movement of this electron in this side, they acquire double bond. And in case of CH2CH, single bond CH2 negative, if negative charge is shifted in this direction, then pi electron shifted in the backward direction and CH2 CH CH2. So, resonance hybrid, this is very interesting example. Ozone molecule, in case of ozone, oxygen double bond length is 121 picometer and single bond length is 148 picometer. Due to movement of pi electron in this side, the double bond becomes single bond and single bond becomes double bond and lengths are same. But on the basis of data, both the CO bond lengths are same and this is possible with the help of resonance hybrid structure. In resonance hybrid structure, both the O bond lengths are 1.28 picometer. Then why? Because of resonance, because of delocalization of pi electron. So, this structure of ozone is not explained by a single Lewis structure. This one is explained by two canonical structure or two resonating structure, and intermediate structure of these two is known as resonance hybrid structure. So, basically if a single molecule is not explained by one Lewis structure, is explained with the help of resonance hybrid. Similarly, another example is nitrate radical. In case of nitrate radical, NO3 minus, and we know a very simple technique. If one negative means one single bond and remaining two bonds are double bond. In this case, the movement of sigma electron and movement of pi electrons, the total number of bonds are 3. So, 3 resonating structures are possible. In this case, the length of nitrogen oxygen single bond and nitrogen oxygen double bonds are different, but on the basis of 3 canonical structure or 3 resonating structure or 3 contributing structure, the resonance hybrid of nitrate is this, in which pi electrons are delocalized and the negative charge is equally distributed on all 3 oxygen atom, like 1 by 3, 1 by 3, 1 by 3, 1 by 3. So, finally, minus 1. So, negative charge is delocalized on all the 3 oxygen atoms. Similarly, in case of carbonate, carbonate is a very important example. In this case, 2 negative charge. It means 2 oxygen contain single bond. So, delocalization of pi electron, only 3 structures are possible. In first case, CO bond, again due to delocalization, CO comes in second bond, and due to this delocalization come in this side. So, 3 structures are possible. In this case, again carbon oxygen bond lengths are different. Single bond have a different bond length, double bond have different bond length, and triple bond have different bond length. We know that in carbon dioxide, carbon connected with 3 oxygen with 1 double bond and 2 single bond. On the basis of contributing or canonical structure, this is the resonance hybrid structure, in which the 2 negative charge is equally distributed on all 3. So, stability of carbonate on the basis of delocalization becomes more. Then, what are the rules for the resonance? All the canonical form, this is very important, all the canonical forms or resonating structure or contributing structure must have proper Lewis structure. It means the number of atoms are same, number of electrons are same, number of bond pair and lone pair are same, only the position of atoms are different. The first point, the position of the nuclei of the atom must remains the same in all the structures. And third point is again very important, all atoms taking part in the resonance, especially pi electrons of resonance, must lie in a plane so that orbitals overlapping for resonance becomes parallel to each other. This is very important point. And the energy of actual molecule is lower than of any form, therefore, delocalization is a stabilizing phenomenon. This is again very important line. Delocalization is a stabilizing phenomenon. It means delocalize electron, stabilize the molecule, increase the stability. All canonical form do not contribute equal to the true molecule. The more stable is a structure is, the greater contributor it is to its resonance hybrid. Then this resonance is a structure. With the help of resonating structure, we are able to calculate the bond order by a simple formula. Bond order for resonating structure, total number of bonds formed between 2 atoms in a structure divided by number of resonating structure. For example, in case of sulfate radical, there are 4 resonating structure and sulfur forms single bond, 2 single bond and 2 double bond. So, total number of bond 1 plus 1 plus 2 plus 2 divided by total number of resonating structure. So, 2 to 4 to 6 divided by 4, 1.5 is a bond order. Then resonance energy, again very important. Resonance energy, basically resonance energy is the difference in the energy of the most stable contributing structure and resonance hybrid. So, resonance energy mathematically actual energy minus energy of most stable resonating structure, and this is the resonance energy of benzene is 150 kilojoule per mole. Then resonating structure is able to explain the stability of the molecule also. Stability in terms of resonance means stability of a molecule is directly proportional to resonance energy, and more is the number of covalent bond in a molecule, more will be resonating energy. This is a very important point, and resonance energy is directly proportional to resonating structure, but this point is not true in all the cases. They depends upon the atoms containing negative or positive charge. If during the resonance electropositive element carry electropositive charge and electronegative element carry electronegative charge, then that contributing structure is more stable. So, this point is explained. Again I am going to explain by giving another example. And some important notes: the canonical form have no real existence. Canonical form have no real existence. There is no such equilibrium between the canonical form as we have between tautomeric form. Tautomeric form means ketoenol tautomerism, used generally in organic chemistry. And next point, the molecule does not exist for a certain fraction of time in one canonical form and for other fraction of time in other canonical form. These are the very important points. In a molecule such as has a single structure, which is the resonance hybrid of the canonical form and which cannot be depicted by the single Lewis structure. So, these are the very important points of resonance. Then I am going to explain why the stability of resonating structure, number of stability is not directly proportional to the number of resonating structure. For example, acetic acid. Suppose acetic acid CH3C double bond OH. We know that in acetic acid, this OH bond, oxygen and hydrogen bond, oxygen is more electronegative. So, this pair of electrons shifted towards oxygen, and acetic acid loses one hydrogen due to rupture of OH bond, and oxygen contain 6 electrons and 1 negative charge, because the dot is gained by hydrogen and H plus is released. So, acetic acid after the removal of one hydrogen gives acetate ion, and acetate ion is resonance stabilized like CH3 C double bond O. Oxygen contain 4 electron, or in this case oxygen contain 7 electrons. So, due to movement of this electron in this side, the pi electron shifted in this side, and CH3 C oxygen acquires single bond, and this oxygen acquire a double bond with 4 electrons. So, on the basis of these two contributing structure, acetate ion give a resonance hybrid structure, equivalent structure CH3 C, 2 single bonds and pi electrons are delocalized, charge distributed equally, minus half and minus half. So, this is the resonating structure, and acetate ion have 2 resonating structure. In this case, both the oxygen atom carry negative charge, and in case of phenol basically phenol is also known as carbolic acid. In case of carbolic acid, phenol loses one H plus ion due to rupture of this bond and becomes phenoxide ion, and phenoxide ion contains one negative charge. So, phenoxide ion is again resonance stabilized. In this case, oxygen, this pair of electrons shifted in this side due to plus R effect, and this one is shifted in this side. So, phenoxide ion exhibit different resonating structure. This is very important. Oxygen acquire double bond and they contain 4 electrons. Then shifting of this electron in this side, when this one is shifted in this side. So, finally, in this case, this one is acquire a double bond, 2 electrons with minus sign, double bond O, then shifting of this charge in this side and this one in this side, and finally, double bond is shifted in this side and charge finally in this side. Again shifting of this electron and the structure becomes like this. And the real structure is again regenerated. So, number 1, number 2, number 3 and number 4 and number 5. So, 1 and 5 are nearly same, only the position of bonds are different. Then the main question is why the stability is not directly proportional to number of resonating structure. Like in acetate, there are only 2 resonating structure, but in case of phenoxide, there are 5 resonating structure. But acetic acid is more acidic than phenol. Why? Because in case of acetate, negative charge is localized on negatively charged atom oxygen in both the resonating structure. But in phenoxide ion, the negative charge is localized in structure 2 on carbon atom, structure 3 also on carbon atom, structure 4 also on carbon atom, only in structure 1 negative charge at oxygen atom. So, resonating structure is directly proportional to stability is not true in all cases. So, stability is directly proportional to number of resonating structure if electronegative atom carry negative charge and electropositive atom containing positive charge. So, thank you for watching. In next class, I am going to explain another topic.